Welcome back to class 8. We're continuing on with the polytropic process. We talked about this in the last video. I talked briefly, I showed you my cheat sheet that I think I'll hand out, even though I'm wondering if that's the right idea, but I'm going to do it anyway. Of all these different processes. And right here is the polytropic closed process that we'll see that we'll be using. All right, so here's an example 3.6, and it talks a little bit about different processes as we go through. So we're going to consider a system, the gas in the cylinder. Consider it as a system, the gas in the cylinder shown here. And you got little tiny weights in there. The cylinder on top of this thing. The cylinder is fitted with a piston on which a number of small weights are placed. The initial pressure is 200 kilopascal, and the initial volume is 0.04 cubic meters, right? So here's 4 different scenarios that are taking place onto the thing, and this right over here steals all the thunder by showing you what's happening. So first off, we're going to let the Bunsen burner be placed underneath the cylinder and let the volume gas increase to 0.1. So it's going to go from 0.04 to 0.1 cubic meters while the pressure remains constant. So the idea here is the pressure is going to remain constant because you left all of these onto this. And so the downward force, the weight of the piston, is always constant and the area is constant. So the pressure must be constant. So in this first process, this is going to be an isobaric. So just keep that in mind. We're going to give these things names. So that's going to be isobaric, and spoiler alert, it's going to be a straight line horizontally on a pressure versus volume graph. All right, so let's do part A, and then we'll talk about part B afterwards. So we recognize that P1 is equal to P2, and it's isobaric. I always think of bar because that's a unit of measure of pressure. Especially in SI, use bars. So I think of isobars. It's probably some Latin derivative for pressure of some sort. So V1 is equal to 0.04 cubic meters. V2 is equal to 0.1 cubic meters. And these pressures are equal to 200 kilopascals. So if we're taking our work from 1 to 2 is equal to P dV, right there from 1 to 2, we can take the pressure, right? So that's just, so we can move the pressure to the outside and we just have V2 minus V1. Anything else you want to say about that? No, I think I'm okay. And so we're going to have our 200,000. And that's going to be newtons per meter squared, and we're going to multiply it by meter cubed, so we're going to end up with a Newton meter. So we know we have our units in check. So we go 0.1 minus 0.04, and so what we're left with is the work between 1 and 2. Oops, that's how I usually do it in dynamics. I draw them that way. I guess this book says that, right? We end up with 12,000 Newton meters, and we know that that equals 12 kilojoules. As a Newton meter equals a joule. So let's take a look. That's A right there. So that's how much got done, right? So we're basically, what we're doing is we're figuring out what the area is underneath this PV, and that was pretty easy to do. Let's take a look at the other ones though. We're going to consider the same system, but at the same time allow that the Bunsen burner is under the cylinder and the piston is rising. We're going to remove the weights in just the right kind of way so that the temperature remains constant Okay, so these ideas right here, it's important ones to try to picture them. Like, what kind of thing would do that? Well, they've given you an example of something that's possible. They've given you an example of how you could have. That's not the only way that could happen, but this is one way that it could happen. That you could have this constant pressure process. Now we're going to do it a special, different way. Someone very carefully and very slowly is going to heat this while they remove these things, while watching the temperature, so the temperature doesn't change. Because remember, PV equals mRT, so, and if the mass were constant right here, you'd have PV over T is equal to a constant. So any combination of those things will be held true right here, so in a process. So just that kind of idea is important. That's why we can go through different paths. All right, so we have B, and so this is going to be isothermal. And we recognized up above that isothermal from the ideal gas law, PV equals mRT, that this right here, if they're all constant, then we're going to have PV equals a constant. Constant. I'm terrible right now. Constant. Okay. Therefore, that means that N is equal to 1, right, of the polytropic. This is polytropic with N. So the polytropic N equals 1. So if we're going to, and if that's the case, we already have this solved for us in the book. So we're not going to, we don't have to go through and do all of this for it. It's not that difficult to do, but since we already have it for this set of conditions, we might as well use it right here. And I'll write down this. Oops, write down this from 1 to 2. And set it equal to P1 V1 natural log and hit to V2 over V1. So once again, we're going to have the units will work out. So we have the starting point right here. And then we have, as the thing is expanding and the pressure is dropping, right? So you can see this line from 1 to right here. That's the one that we're doing. Here's the polytropic process, that curve. Remember, I was describing with these curves, like let's see, let's move that guy over there. See that right there. So that's like the path that it's taking with this is equal to, with the N equal to 1. So we have 200,000 newtons per meter squared, and then the volume 1, which is going to be 0.04, and then you're going to take the natural log of 0.1 over 0.04, and what you're left with is 7,330 Newton meters, or 7.33 kilojoules. You make a comparison, you can see the area is less, but of course that makes sense because what we're really talking about is this area right there, underneath that. And let's see, let's go to the next one, C. Consider the same system, but during this process right here, we remove weights at such a weight that now we get an expression of 1.3. Constant describes the relationship between the pressure and the volume. Again, the final volume is 0.1 cubic meters. So now we want to calculate the work. So in C, this is a polytropic, where N is equal to 1.3. At 1.3. And one thing you would be helpful for, I mean, if we could look up the equation for this, might be equation we want to look right here. It's this equation right in here. P2 V2 minus P1 V1 divided by 1 minus N. You can also look it up as I had shown in my thing right here. Here's the polytropic process. And the work on a per mass basis right here. So you see this is the same, let's see, little marker, the whole thing here. This is the same thing. They just reversed them, but they reversed this as well, right? So you'll see that we have P2 V2 minus P1 V1 divided by 1 minus N, so you get the same thing. Just figured I would point that out. So we need P, in order to use this equation, we need to know what P2 is. We already have P1 and V1. We need P2. So we'll go ahead and use this relationship right up here to be able to find that P2. And we find that P, so what we would say, let me put it this way, P2V1 to the N equals P1V, I'm sorry, that's a 2, 1 there to the N. Okay, and we know that N here. So if we want to find P2, what we do is take P1, multiply it by V1 over V2 to the N, which is going to be 200,000. Did I do this right? Times V1 0.04, right? 0.04 divided by 0.1 raised to the 1.3. And did I lie before? I think I might have lied. No, I didn't. Okay. What I end up with is 60,773 newtons per meter squared, or 60.773 kilopascals. But now I want to get the work between 1 and 2, PdV, right here, from 1 to 2, and set that equal to, here's the equation that we found, P2V1, put lines on those, minus P1V1 divided by 1 minus N, or 60,773 times 0.1, yeah, minus 200,000 times 0.04 divided by 1 minus 1.3. All right, so this up here is going to be negative, and that's going to be negative down below. So what we find from the work to 1 to 2 in this situation is we get 6,409 Newton meters, which is 6.41 kilojoules. And we could compare it to this 7.33, or compare it to this 12. You can see also on here, it's underneath, this is the area underneath it. So it's going to be slightly less, which it is right there. We have one last thing to take a look at, and this is a constant volume process. So we consider the system and the initial state given in the first 3 examples, but let the piston be held in place with a pin, right? So we'll put a pin right in there. So it can't change volume. In addition, let the heat be transferred from the system. So we're going to steal it from the system and allow the temperature to go down, or allow the pressure to go down. And what you're dealt with is this line right there. And you can't have any area underneath that. So in D, I should write this out the right way. The work between 1 and 2 is integral of P dV, but is equal to 0 because dV is equal to 0. There is no change in volume. Therefore, work from 1 to 2 is equal to 0. Well, I guess I already wrote it over there. But anyway, these are processes, and there's a bunch of them. And they're not crazy complicated, but using them is one of the primary tools that we have to first analyzing, then even designing thermal systems to generate power. See you with the next example.